So we'll start in 1929 when Fermilab sought to explain the stability of matter. And so at this time, there was only two known particles. So there was the proton and the electron. And so this was presented as the conservation of charge. And so if you read his paper, it says, instead of one law for the conservation of charge, we must have two, expressing the conservation of the number of electrons and protons separately. So this was one of the first attempts to classify the conservation of baryons and leptons separately. But like I said, there was two particles, proton and electron. So then over the coming decades, as we discovered a lot more particles and our understanding of the subatomic world expanded, in the 1950s, Zweig and Gaumain independently developed the concept of baryon number and quark triplets. So if you read this paper from Gaumain, it says this, we get around by assigning baryon number 1/3 to each member of the basic triplet. And so a baryon is a group of subatomic particles that are subject to strong force and are composed of 3 quarks. And so if we put this information together, we can end up with what is known as baryon number, or B. So this quantifies the number of protons and neutrons in a system. So the formula is B equals 1/3 times the number of quarks minus the number of antiquarks. And so if we look at this in terms of a neutron and a proton, you can see that there are 2 down quarks, 1 up for the neutron, 1 down, 2 up for the proton. So this makes the neutron slightly more massive than the proton. So the neutron can decay, but proton has nowhere to decay as long as this baryon number here is conserved. So baryon number has also never been observed to be violated in any experiment. So then the natural question is, can it be violated experimentally? And so to answer this, we can look at the standard model. And so the standard model is a theoretical framework that describes particle interactions. And so if we write up the gauge structure of the standard model, you have the SU3, the SU2, and the U1. So these represent the 3 different forces. So you have the strong force, the weak force, and the electromagnetic force. And their conserved quantities are color, isospin, and then charge. So these are what dictates the way that the particles in the standard model interact. So we can also write out the accidental global symmetry. So this is in terms of baryon number and leptons. So here your symmetries would be baryon number and lepton number, and your conservation of B and L. And so this is accidental, and what that means is that it arises not from a fundamental requirement of the model, but rather as a byproduct of the way the standard model gauge structure is written. And because of this, baryon number is not a fundamental conservation in the standard model, but it occurs accidentally. And if we want to violate baryon number, we can go to what are known as grand unified theories. So these naturally predict baryon number violation. So the way that these work, so you have your 3 different forces, the electromagnetic, the weak, and the strong. And then in 1973, the electromagnetic and weak were discovered to be coming together and form the electron-weak interaction. So then theorists decided they could add in the strong force as well, and you end up with what is known as a grand unified theory. And so once you've combined all these forces, you've unified the forces, this opens up the possibility of transition between quarks and leptons. So now the proton that was the lightest baryon has other places it can decay to, it can go somewhere. So this opens up the possibility for baryon number violation. And there are 2 main types of grand unified theories of non-supersymmetric grand unified theories. So the main prediction here is proton to positron. Then you have supersymmetric grand unified theories, where the main prediction is proton to charge tan. So detecting either of these signatures would provide strong evidence for a grand unified theory. But the question is, why do we care about that? And to answer that, baryon number violation is also an essential ingredient for baryogenesis. And while proton decay can't directly address baryogenesis, it can serve as a flag bearer for grand unified theories, which have other means to violate baryon number to answer baryogenesis. But what baryogenesis is it tries to answer the question of why is there matter, antimatter imbalance. And so if we look at this cartoon here, you have matter in blue, antimatter in red. And so from particle experiments, we know that whenever matter is created, we get an equal part antimatter. But then when matter and antimatter come together, it annihilates and leaves behind only energy. And so then the question is why, when we look out at the universe, do we only observe matter? And this is what Biogenesis seeks to answer. Where did all the antimatter go? So in 1967, Andrei Sakharov tried to answer this, and he pondered this quandary. He came up with 3 conditions that must be met to explain the missing antimatter. First, there must be charge and charge parity violation. So this prevents equal production of baryons and antibaryons. The second is that there must be interactions outside of the thermal equilibrium. So this allows processes to happen without reversing. And third, there must be baryon number violation. So you must have more baryons produced than antibaryon. So with these 3 conditions, have any of them been met? We can look at first. So this was discovered in 1964 by Proton and Fitch and neutral hand decays. The second was also discovered in 1964. So this was with the cosmic microwave background. It was discovered that the universe evolved out of equilibrium. And then we have one final condition, which is baryon number violation. And despite decades of searching for it, we've yet to discover it. So how have searchers gone about looking for baryon number violation? The early days, they used what are known as indirect methods. So an example of one of the first was this old Soviet paper where they looked for the spontaneous fission in thorium-232. So you would observe thorium, and then if it spontaneously fissioned, that would mean one of the nucleons in it would have decayed. So this is not the most ideal way to go about searching for nucleon decay, because you're very limited in terms of your material. And so this was soon replaced by what are known as direct methods. And so in direct methods, you would obtain a large vat of whatever material you wanted to search. And so you can do water, liquid argon, liquid scintillator, etc. And so then you would observe your detector medium and search for a specific decay mode. So the first ever attempt at doing this was in 1953 with Project Poltergeist. It's the same experiment that was the first to detect neutrinos. It wasn't very effective as it was only 30 meters off the ground, so you had a vast amount of cosmic rays. But it was the first attempt to detect proton decay, but a direct method. So, like I mentioned earlier, in 1973, the electroweak force was discovered. That spawned the creation of grand unified theories. And with this, you had the prediction of proton decay. And so a lot of experiments spawned out of this. They wanted to see if they could detect it. And so some of the early ones, you had Sudan, which was an iron calorimeter that was built in Minnesota. You had the IMB detector, which was a large water trinket detector. And then you also had Freyas in France and Kamiokande, which was in Japan. So these experiments were the first ones that really started searching for all these different branches of proton decay. And then the successor of Kamiokande was Super K. It's that you can see here. So it was a bigger version of Kamiokande. And any mode here that it essentially searched for, it was able to set the limit on because it was so much bigger. But despite all of these efforts, we've yet to discover proton decay or baryon number violation. So where do we go from here? Well, we build bigger and better detectors. So the future, we have Juno. So this is a liquid scintillator detector being built in China, which you can see here. You have Hyper K, which is a water trinket detector, which is the successor of Super K. So it's 190 kilotons. Then you have DUNE, which is a 40 kiloton liquid argon time projection chamber, which would be built in the US. So if you look at these 2 figures here, so this is proton to positron. So this is the non-supersymmetric prediction. And then proton to charge pan. And this way you can see all the different grand unified models and their predicted limits for the proton decay mode. And you can see with the proton to charge pan, the limits are much lower compared to positron. And these colored bars show what predicted sensitivity for these experiments are. And so going forward, I'll focus on the Deep Underground Neutrino Experiment, or DUNE. So DUNE is a broadband neutrino. It has a broadband neutrino beam, and it'll start it out at Fermilab. And it'll shoot some neutrinos all the way out to South Dakota, which will be a mine in the Sanford Underground Research Facility. So it's a large international collaboration. So there's 1,400 plus collaborators, 200 institutes in 30 some countries. And so the way the Deep Underground Neutrino Experiment works in a similar fashion to other accelerator neutrino experiments is you'll start out with a proton accelerator. You'll produce some high energy protons, you'll slam them into a target, and then that'll produce some charged particles that will get focused by magnetic horns. Then you'll end up with a beam of neutrinos. Where your charged particles will decay. In the decay tunnel, you end up with neutrinos that will then travel to your far detector. So DUNE's goals with accelerated neutrinos are to study leptonic CP violation, to determine the mass ordering, and to test the PMNS matrix unitarity. But we can also measure other sources of neutrinos. So you have supernova, solar neutrinos, as well as atmospherics. You have many sources of neutrinos that can be studied. And you can also search for new physics, such as proton decay, stereoneutrinos, neutron-antineutron oscillations, etc. So the way that the far detectors will be built, so you'll see here, this is a photo of the Stanford Underground Research Facility above ground. And if you take a cutout, this is what you'll see. So everything that we built with the DUNE detectors down here will have to travel down what is known as the Ross shaft. And so this is also the same mine where Ray Davis did his solar neutrino experiments way back in the day, which you can see here. So, like I said, everything that will be built in these detectors will have to travel down this mine shaft, which is quite small. So you can see that shaft here. So it's 1.4 meters wide, 3.5 meters long, 3.6 meters tall. And so to build a massive detector underground, everything needs to be small to begin with. And the detectors that would be built will consist of two different types of technology. So you have the horizontal drift that will look like this from the outside, where you have field pages and CPAs. And so you'll have 4 different drift molecules, 4 different drift volumes inside of the horizontal drift detector. And the readout electronics will be in anode planes. These are wrapped wires. So there'll be thousands of wires that will be wrapped per plane. So they're very delicate. So they're easy to break. And you'll have 150 of these APAs that will make up the entire detector. The other detector technology that will go into South Dakota is a vertical drift module. And so in this, you'll split the detector into 2. So you have a top drift volume and a bottom drift volume. So instead of the delicate wire wrapped anode planes, you'll have charge readout boards, which are PCB based. And some of them will be produced here at Yale. And so this is more robust, and you also have a more active volume because you have fewer detector pieces inside your craft stack. So these are what the far detectors will look like, but it's essentially building a ship in a bottle because you're 1.5 kilometers underground, and everything has to start out small. So if you want to use a man lift, you have to take it apart and put it back together. And so large-scale prototyping is mandatory, and so that's what has taken place for the DUNE Far Detectors. So this allows you to do integration tests with one-to-one components, validate the installation, estimate resources needed, validate design, as well as assess performance. So this prototyping takes place at the CERN Neutrino Platform, which you can see here. So at the CERN Neutrino Platform, you have 2 different cryostats. You have the NPO2 and the NPO4 cryostat. So the NPO2 is where vertical drift technology is prototyped, and NPO4 is where horizontal technology is prototyped. So these are both based off of liquid natural gas tanker technology, the same technology that will be used for the far detector. So there's been 2 different generations of prototypes at CERN. So you have the first generation, which operated from 2018 until 2022. And so the single phase, the horizontal drift version of this, ran from 2018 to 2021. You can see here an image inside the cryostat. You have your anode, your field page, and your cathode. So the cathode is what will have the high voltage that'll pass 180 kilovolts over to field cages, and that'll slowly be stepped down until you get to your anode. You can see all the wrapped wires and the reflection in this image here. So ProtoDUNE-2 built upon what was done in ProtoDUNE single phase. And so it was built in 2023, 2022 and 2023. and operated in 2024. And here you can see an image inside of this. So you have the same style of technology, you have CPA, field gauge, and APA. There is visual difference here, so you can see there's less FRP material, so fewer insulating material here than you have up here. The first generation for the vertical type technology was ProtoDUNE dual phase. That ran from 2019 until 2022 in a couple different versions. And then ProtoDUNE vertical drift was built in 2023 and this year, and its operation will begin in the future. But the vertical drift first ProtoDUNE was the dual phase. And so here you had a cathode at the bottom, a field gauge, and a charge readout plane. So this is the PCB-based readout. And at the top, you also had what was a gaseous argon phase, and this is a singular drift volume. So you would need a very high voltage to carry from here all the way up to there. And then the vertical drift you split in two, so you have your CPA, your PA as well. So the way that these detectors operate and ProtoDUNE, so you split the cryostat in two for horizontal drift. So your high voltage is your cathode. So in this case, it's at 180 kilovolts, and then you step it down across field gauges to your anode. And for dual phase, you had to start at the cathode at the bottom, and then you went all the way up to the top of the detector. So then you had your gaseous argon phase, and so here you needed twice as much high voltage because you needed to carry the field all the way to the top. The vertical drift took the best parts of dual phase and horizontal and put them together. So you now split the detector in two, so you don't need as high voltage, which was an issue with dual phase. And you also got rid of the gaseous argon, and you have the PCB-based readout. So going forward, I'll focus on the horizontal drift technology. So for ProtoDUNE single phase, it looked like this. So we had a 3.6 meter drift, 7 meters in the Z. This is the direction of a beam, and you had 6 meters tall. So this is half the height of what the final detector will be in South Dakota. And you also have the wrapped wires. So there's 3 different wires. You have your U, X, and V. And so, like I said, you have the cathode sitting at 180 kilovolts, and this will be passed onto the divider boards and slowly stepped until you get to the end, where it'll be near zero for the APA. So the way that this detector works in practice, you can see here in this cartoon, where you have charged particle track, and it gets drifted over, and you end up with your 2 plane readouts. So ProtoDUNE single phase was validated with beamline data, and at the time that it was built, it was the largest liquid argon time projection chamber in the world. So it was connected to CERN's H4 beamline for charged particles. So there were various different particles that were collected, and this was over 8 weeks. So you have pions, protons, electrons, and kaons, and this was the first beam event for ProtoDUNE single phase. And with these different particles, you were able to conduct a lot of different analyses. And an example of this is the kaon analysis. So this was the first total inelastic cross-section of kaons at high energy for argon. So if you're in the DUNE experiment, you can read the tech note, or you can find the paper that's come out. But these are some displays for this analysis. Here you have a kaon coming in. It's going to scatter off argon nucleus here. You can see that taking place. This shows the reconstructed track length for the beamline kaons. And so you'll notice that the black here is data. Then there's this big spike, and then there's another spike, and another spike at the end here. So the spikes are caused by electron diverters. And so the idea was that you didn't want electrons to drift between the APAs. And so you installed electron diverters to push those electrons away so that they'd still collect on wires. But those ended up being grounded, and so they attracted electrons as opposed to pushing them away, and you end up with broken tracks. And this is the kaon cross-section compared to Genie and Geo. So ProtoDUNE single phase demonstrated the cryostat design derived from LNG technology, and it matched or exceeded all of the design specifications that DUNE required. So you could take that design and could install it in South Dakota, and it would have met all the TDR requirements. And then also demonstrated DUNE for construction abilities and provided a lot of data for analysis and publications. And ProtoDUNE 2 built upon this by using lessons learned. So you got rid of the electron diverters, you improved the high voltage, introduced field gauge profiles, improved cold electronics, amongst other things. And so I showed earlier, ProtoDUNE single phase is half the height of final DUNE Far Detector. And so you have two different versions of the APAs. So in DUNE, they'll be stacked on top of each other. So you have a top and bottom. So in ProtoDUNE 2, you test both of those. So they'll be both designs. And then you also have new calibration systems like laser calibration, amongst others. And so ProtoDUNE 2 demonstrates the final production. It's module 0 for the horizontal technology. So it allows you to finalize production and assembly and the way that things will go and stuff like that. So I was heavily involved in high voltage, so I'll discuss some improvements that were made from ProtoDUNE single phase to ProtoDUNE 2. And so here you can see the ProtoDUNE single phase design, where there's a lot of insulating material on the exterior of the field cage. So then with ProtoDUNE 2, you got rid of a lot of that material. So you made it lighter, more robust, as well as cheaper. And in addition, you introduced what are known as the bit profiles. And so this is something I worked on for a long time. You've been the aluminum profiles at the edge of the field cage. And the reason you're doing this is if you look here, you can see the straight profiles that are used in ProtoDUNE 1 and the bent ones that are in ProtoDUNE 2. So this is the same design that's in SP and D. You can find the box bin for this down in the highway, I found out. And then the electric field uniformity is shown here. So in the yellow is greater than 1% nominal and blue is within. So the blue is what you're aiming for. And since ProtoDUNE 2 serves as module 0, so you're going to test the installation and the way things are going to proceed in South Dakota, I'll go over how you can assemble an end wall, since this was a large part of what I did over at CERN as well. So you start with the production of the large components. So we built this large ultrasonic cleaner. You needed a way to clean these large box beams. Then you bend the profiles. So once you have your parts, then you can build your panel. And then you can store it on what are known as roller bases. So you can move them around. Then you mount your divider boards. So when the cathode passes the high voltage off field cages, it's these sets of resistors that are slowly stepping it down. So this assembly was much quicker than ProtoDUNE single phase, as well as a lot simpler. And so once you have your individual panels, you need to build the actual detector. So you have 3 different modules here. So you have the top, middle, and bottom. For DUNE, you'll have the top, 3 middle, and a bottom, 4 middle. And so each end wall in ProtoDUNE consisted of those modules. And so then you have to have a hanging structure for these to hang from. And so here you build that. And then for ProtoDUNE, you fly it over to the cryostat, the clean room, sorry. And then that'll be lowered down and you'll attach it to your top panel. You lift that up, you'll attach the middle, and then you'll attach the bottom. For DUNE, you won't fly it over with a crane, rather you'll use a winch system. So you'll build the hanging structure right above it, winch it up, attach the modules in the same fashion. So for ProtoDUNE, then you have your full module built and you fly it over to the clean room and assemble it and put it into the cryostat. You can see this modification here. So this is for beamline. So I won't go into all of these details here, but this is the timeline of the construction of ProtoDUNE 2 from a high voltage perspective. And so these are all the different tasks that we're part of. So you start with end wall production. So you bend your profiles, procure all your parts, and you assemble your CPA, your end wall, do quality control work on the divider boards, and you install your field cages and end walls, test your deployment, do final divider board QC within the cryostat. Then for ProtoDUNE, you install a beam plug, since it's a charged, there's a charged beam that's going into the detector. So for DUNE, you won't have this, but you want to make sure that your particle beam actually gets into your detector. So you need to have a beam pipe. And then once your final electrical connections are made, so between end walls, APAs, CPA, et cetera, then you can make sure everything is in planarity. You see your cryostat, build up with liquid argon, and then you can obtain your first data. So ProtoDUNE 2, similar to ProtoDUNE single phase, operated with beamline operations. And so liquid argon completed filling in April. Then your first week of beam was in June. And the high voltage system had essentially 100% uptime throughout. And you had 10 weeks of beam data with both positive and negative polarity. And then there were also some neutrino events that were detected recently. So there's upstream beamline events, and then those were producing some neutrinos, and actually detect those and protocol. So this is one of your first events from the beam. This is an example of reconstruction of the event. So ProtoDUNE campaign for the horizontal drift is essentially ending its completion as ProtoDUNE single phase beam is done, and it'll run for maybe another month or so before the liquid argon will be passed over to vertical drift. And ProtoDUNE single phase validated the design, met all the requirements, and then ProtoDUNE 2 made key improvements to it. And both detectors measure beam. And so with the conclusion of the ProtoDUNE campaign, we can look ahead to what we can do with full-scale DUNE physics. And so this includes things such as baryon number violation, neutrino physics with the accelerators, astroparticle physics, etc. And so the rest of this talk will focus on the baryon number violation with the DUNE Far Detectors for the channel Proton to charge pan. So this mode is known as the golden channel. And the reason it's known as the golden channel is because it is the dominant mode that's predicted by grand unified supersymmetric grand unified theories, but it's also a mode that liquid argon detectors have a distinct advantage over water Trinket detectors. The reason being, this charge can is invisible to water Trinket detectors like super K or hyper K because it falls below the Trinket threshold. So some key features of this channel are you'll get a distinct signal here. So you have the can that'll come forward and it'll break peak around here. Then you have the muon come out, and then you'll have an electron come out. So you have this distinct looking signature in this cartoon. There are some difficulties with this. So the argon atom is not a small nucleus. So when the proton decays, the can is going to still be living in the nuclear environment. It's not in the detector to be detected yet. So it has to travel through that nuclear environment to get to the detector. And in doing so, it can undergo what are known as final state interactions. So this can cause your can to lose energy. You can have nucleon knockouts. It can complicate the reconstruction. And in addition to this, there are some backgrounds that can mimic your signature. So an example of those is quasi-elastic, like charge current scatters, where you can have a neutrino come in, it'll knock out a proton, then you have a muon and an electron come out on the other side. So if we purely look at the right-hand side of these two cartoon images, you'll see a muon, electron, muon, electron. And so those can look very similar to each other, with the key difference here being the can will break peak around here, and the proton will break peak out here. So if you can properly reconstruct the direction of those particles, you can use that to differentiate them. Now, to not look at a cartoon image, you can see here as an event display of some Monte Carlos. This is your can, muon, electron. So this is a signal-like event. And then this is a background that mimics that. So you have your proton, muon, and your electron. And you can see how they look very similar. So for the simulations that I've used for my analyses, they're created with Genie version 3.06. So Genie is an event generator. So this is not the most recent version of Genie, because these samples are a few years old now, but you use Pandora reconstruction with this. And so that's a reconstruction algorithm that's used in liquid argon detectors, and it's without a beamline assumption. So the default Pandora assumes you have beamline particles. And so to get rid of that, you perform better for atmospherics. And so in Genie, I utilize the proton decay module for proton to charge pan. And then for the atmospherics, it's the Honda Flux at the Homestake Mine, which is the location in South Dakota at a solar maximum. In addition to these parameters, I have 3 different main nuclear models. So these are what model the Fermi momentum of the nucleons themselves. And so those are the Bodick-Ritchie non-local Fermi gas, the local non-relativistic Fermi gas, and the effective spectral function. So these model the Fermi momentum of the nucleons themselves. Then you have intranuclear cascade models. So like I said earlier, when that can is produced, it's still inside the nuclear environment. So you need to model the transport of it into the detector. So that's done in 2 different ways with these cascade models. So the HA 2018 and HN. So you can put these together and you can obtain 6 different modeling configurations. So to break this down a little bit, so we have the 3 different Fermi momentum models, and you can see those here. So this is the very initial Fermi momentum of the struck nucleon. So this is right before an atmospheric neutrino comes in and strikes it. So the reason you don't see any impact from HA or HN here is this is the very initial state. So there's nothing transporting through the nucleus at the moment. So you can see the three shapes. So you have the local Fermi gas, which cuts off right about 0.3. You have the Bode-Ritchie model. So it's a global Fermi gas with a high energy, high momentum Bode-Ritchie tail. And then you have the effective spectral function, which has a lot of high momentum Fermi motion. So you can look here at the proton. So this is very similar plot. This is the Fermi momentum of the protons right before they decay into your kaons. So once your kaon has been created, so once the proton's decayed, you're inside of the nucleus. And so that's where your intranuclear cascade models come into play. So the HA 2018 is a single effective interaction. So it's based off hadron nucleus data. And so there is no step-by-step interaction modeling. So you'll have a single effective interaction. And HN 2018 is a full intranuclear cascade model. And so you'll model the interactions stochastically. And so you can have multiple interactions inside the nucleus itself. You can see this cartoon here where you can have charge exchange, scattering, absorption, ion production. You can have a lot of activity in the nucleus before you ever get to your actual detector. And so when we look at the effects of these cascade models, you can see here, this is the initial state of the kaon that is born from the proton. You can see this is pretty Gaussian around 0.1. And then if you look at the final state, so this is the kaon kinetic energy right as it gets into the detector, you'll see it shifts towards the lower energy. And you can see a split here between the HA and the HN models. And the reason you observe this is the HA is based off data, and so the only interaction it models is scattering, so you get a larger shift towards low energy. And this can impact things because at these very low kinetic energies, the detector is essentially not able to reconstruct your particles very well. It's almost blind to a lot of these kaons. So the main background is from atmospheric neutrinos, and so these are produced by cosmic rays. So your cosmic ray will come in, it'll interact with the nucleus in the atmosphere, you produce some pions, and then you'll end up with some neutrinos at the end. Because DUNE is built in a mine, you won't get a large cosmic ray background. You may end up with some, but not a whole lot. So the main background would be atmospheric neutrinos. So if we look at the distribution of the events in terms of energy from atmospheric neutrinos, you can see all the different interaction types for the different flavors of neutrinos. And this will serve as a key input for the proton decay background. And so if we integrate this, you can end up with an actual count for the number of atmospheric neutrinos. So this table is a very conservative estimate. So there's no containment requirements or anything of that nature, just purely the number of expected atmospheric neutrinos. So one of the approaches I've taken to studying proton decay is to use a boosted decision tree. And so in this, I use Pandora reconstruction for both proton and atmospheric samples. So I've described the nuclear models, and you produce your background and your signal, you reconstruct it. So then I apply a set of selection cuts. And so for each nuclear model, I apply identical pre-selection. And then I optimize a boosted decision tree for a selected nuclear model. So the model I chose is the HA-LFG. At the time, there was no official DUNE tune of Genie, but now there is. And so that is a local Fermi gas with the high momentum Bode-Ritchie tail attached to it. And so the most similar is the HA-LFG. So that's the reason I chose that as the nominal model. And so then you take those parameters and you apply them to other nuclear models, and you can end up with a spread in terms of your sensitivities. So the pre-selection cuts I apply are based off of this topology where you have kaon, muon, and electron. So I require that there be 2 or more tracks per event. I require that there be 2 more tracks per event. And I have a common vertex between these. So I'll require it to be within 5 centimeters. You want it to be kaon, muon, or muon, electron. And then if, for example, your kaon is not reconstructed or your reconstruction issues, you can sometimes select the muon and electron. Since the core of this is to compare this kaon to the proton, I don't want to have that be a selection. And so I require the short track to be of kinetic energy greater than 38 MeV. And then the final cut is to require that the long track to be between 20 and 80 centimeters. So for the muon coming from the kaon, most of those times that kaon is decaying at rest. So you have a very specific length of a muon track, and your atmospheric neutrino can have a wide spread. So if you cut on this, you can get rid of a lot of background. So here you end up with just about 35% of your signal and about 8% of your background surviving. So then I trained the boosted decision tree. You can see the responses here, where you have your signal and your background. So with the boosted decision tree, then you can obtain. Oh, that's my voice. Sorry. I kind of the comment question. Sorry, I didn't realize that. Okay, sorry. So with the boosted decision tree, you can end up with a rock curve, and so this is a modification on a rock curve. So this is expected background counts for 400 kiloton years. So those tables I showed earlier where you can integrate the atmospheric neutrinos, you can use that to give you your background counts. And this is your total signal efficiency. These are for each of the different nuclear models, where the black is the HALFG model. You can see that there's a spread here. And you can notice the spectral functions kind of tail off over here by themselves and see there's a big difference between the model earlier. Another approach I've taken to studying proton decay is to use a graphical neural network. So this is NuGraph. So NuGraph was developed by V. They're a postdoc at Cincinnati. And so it's a state-of-the-art graphical neural network for semantically labeling detector hits in neutrino experiments. And so it works natively on the hits without modifying the structure. So you have your three planes, so your three wrapped wire planes, and so they'll pass information amongst each other in each plane, and then it'll pass it up, into what is known as a nexus. So you make connections between the different planes. So this slide's not the easiest to follow. So we break it down into a event display similar to what I showed earlier. You can see here, so you have your incoming neutrino, you produce your charged particles, and then that will be drifted over to your wires. You'll end up with your signal. So the signal is your hits, and so this is then put into the graphical neural network. And so this will give you your wires, the wire number, peak time, integral, and your RMS. So this is, the hits are Gaussian fits to the waveforms. And so for microBOON, which is what NuGraph was originally tested on, these are your direct inputs into NuGraph. But for DUNE, you have wrapped wires. And so that means your API can take hits from here as well as over here. So you have to use a different version of hits. So you have your Gaussian hits, those are fed into space points, which are 3D hits, and then you disambiguate those and you end up with 2D hits again. So those hits are then connected in the graph. So that uses Delaunay triangulation. So this allows for long and short connections. And here you can see a comparison in terms of accuracy to other edge types. And so the important thing is to be able to have long connections. So for example, if you have unresponsive wire in your detector or broken wires, et cetera, you can still make connections amongst the hits to, so you don't lose your event. So once you have those collection of hits and you pass that information amongst the planes, you pass it into a nexus node. This is where your space points live. So they're 3D hits and you exchange information between planes. So you end up with an overall image of the event. So here is some different trainings. These are the 6 different nuclear models. So this is a small data set of 40,000 signal, 40,000 background. And this is the recall for the validation. So this is your steps throughout the training. You can see here you end up with about 90% recall. So it's 90% of your proton decay as well as atmospheric neutrinos that get properly classified. Now, this is a confusion matrix for the validation. And so this is showing this recall here, but at the very last point. So you get 91% of proton decay being properly classified and 89% of your atmospheric neutrino. So these are very small training samples, but this is just a comparison of what you get if you train on each individual model. So to really see what you could obtain from NuGraph, I created a larger data set. So this is 400,000 proton decay and 400,000 atmospheric neutrinos that I would use for the training. And here you end up with a much better recall. So you get about 95% of the events being properly classified. So the same confusion matrix you can see here, so you get 95 and 94 as opposed to about 90%. So you improve. Now, if you look at the score distribution, so you can see here, so this is properly classified proton decay events. These are events that are classified as atmospherics. There's a little bit of overlap here, you can see, but it's pretty good in terms of classifying the different events. Now, with your score distribution, you can make cuts throughout. So if you want to see how many proton decays survive here, if you make a cut at 0.1, 0.8, 0.9, etc. As you make a lot of these different cuts, you can create what is known as a ROC curve. So this will tell you your sensitivity at various cut points. And for the HALG, this is what you would obtain for your ROC curve. And so this is on a testing data set of 40,000 proton decay and 40,000 atmospheric neutrinos. So it's a small testing data set. And then if you run it on the unique different nuclear models, you can see here you get a spread. And so this black one is the HALFG. And these other colors represent the other nuclear models. Once again, here you can see that the HN Bode-Ritchie and HN effective spectral function sort of tail off by themselves. I wouldn't draw a lot of physics information from this, but it essentially is showing you the robustness of the model in terms of performance. So in conclusion, the DUNE experiment is well underway. Detector prototypes have been successfully demonstrated at the CERN Neutrino Platform at scale, and good physics has been formed with ProtoDUNE detectors. Both the boosted decision tree and NuGraph independently perform very similar. The boosted decision tree performance, you get about 16.8% signal with 0.69 backgrounds per 400 kiloton years. And the initial performance in NuGraph shows very similar performance, but it's still, I think there's still a lot of room you can improve with that. And then past studies have used the CNN plus boosted decision tree. And so building on this, combining both boosted decision tree and graphical neural network, something that will be explored as past studies, for example, the CNN, not performed as good as the graphical network, but when you put them together, you can obtain a better overall performance from what we've seen historically. So thank you for your time. I can't give you a better conclusion because DUNE won't let me, but maybe in the future, do my piece.
Any questions?
I'll start this off with, I'm not an expert, but how does that map onto sensitivities for proton decays that exist? I'm not sure how to convert 16% to, like, is this competitive with what's out there that we know?
It's better than what SuperGay has put out so far. If you compare it to, say, for example, the predictions for Hyper-K, I don't think anyone's really going to compete with Hyper-K, purely because it's 190 kilotons. It's 5 times bigger. So you have 5 times as many protons, but it is better than what the current limits are that are out there.
Okay, so I have 2 questions, so that's okay. One is more hardware. So what's the advantage of having the vertical drift over horizontal?
So one of the key things is, so there's a large issue with quality control with the APA because they're very delicate with the wires, and so that's one of the motivations why they swapped the order of the DUNE Far Detector installations. And in addition, you also have more active volume because you have 2 drift chambers as opposed to 4, so there's less detector components inside of it. It's like the perfect world, you'd have a dual phase or just a singular drift. But to do that for DUNE, you'd have to have 600 kilovolts of high voltage, which is not really feasible. And so if you split it in 2, you need 300, split it in 4, it's 180. And so if you have a larger drift volume, you have more active volume, and then it's not as delicate in terms of the readout.
Okay, and then this question, so would you think about this one? When you think about the atmospheric neutrinos, do you expect it to be isotropic, like equally likely to come from like through the earth and then through the mountain?
I think you would, yeah, you should expect probably similar of what you're.
Thanks.
So, sorry, yeah, okay. So I guess just with your conclusion, like, I have a hard time thinking of it in terms of like, since you have some false positive rate with machine learning or any method you use, how many events would you have to get before you say definitively, like, we found it, you know, like, what would be the signal that you're looking
So conclusion's big on purpose. I'm not allowed to give the conclusions, but so you'd want to so if you have zero background counts expected and you observe something, for example, then that would be your ideal scenario. So with here, for example, you have 0.69 background counts performed in 10 years. So if you were to observe a signal, just yeah.
On that point, before we go, perhaps Natalia, can you say a few more words about what motivates the 400 kiloton years?
So that's what has been used historically. So it assumes 10 years of 4 DUNE Far Detectors running. So for pretty much all sensitivity studies or simulation studies with Far Detectors, that's been the baseline assumption is that you have 4 Far Detectors for all Far Detectors. Yeah.
You only have 0.69.
Well, one of my questions was actually the last one, so that's great about the, like, what kind of false positive rate would you need, but I think that basically answers it. And then the other thing I was wondering, this might be too far afield, but it was about the intranuclear cascade models and the one that was based on data.
Yeah.
So is the idea that they use data from other interactions and then kind of interpret or extrapolate them for what would happen in the case of proton decay? And also, I guess my other question is, I didn't quite understand when you were showing the plot with the differences between these two models, whether that suggested that one is working better or whether that's kind of unknown. I might have just missed that.
So the HA model is based off hadron nucleus scattering data. So you have protons scattering off nucleons, et cetera. And so it's coming from hadron nucleus scattering, like actual beamline data and stuff like that. So that's used grades. I believe they're tables, and then you kind of obtain your final state prediction from that.
But those things, sorry, it's a follow-up on that one, clarification. That one, does it have the argon itself? Because or just lighter nuclei and then it gets extrapolated to what argon is like?
That's a good question. I'm not sure off the top of my head what their data set they use is.
Sorry, and then just the second part of it was if you go to the next slide and you have the differences at the low energy. So is that because an effect is missing essentially when you just look at the scattering data?
So it's hard to say what the actual way to model the nucleus is. So the HN is more theoretical. So it's kind of based off what you could have in terms of interaction. The HA is what's used usually because it's based off data, so you can reweight it, for example. But yeah, so there's different ways to go about it if you want to do things. But the HA is usually what's used by experiments.
Thank you.
Yeah, so next up, in terms of systematical errors, what do you expect to be the greater source? Would it be from theory or from your understanding or misunderstanding of your detector response?
So that I feel like that would depend per se. So like a lot of studies have, like even this one, it's based purely off one detector type, and DUNE will eventually consist of 4 detectors of potentially different technology, so that could introduce a lot of frequency. But then you also have your uncertainty on your signal and stuff of that nature. But then also in terms of the modeling, you don't know what it is in the proper model. So I think it all kind of plays a role in terms of what your overall final uncertainty would be. Yeah.
But if you were to quantify, I guess, what are the differences between the different models? Are they factors of 10 or are they at the percentage level?
So if you calculate the limits for the different models, you can end up the spectral function from the BDT, you end up with quite a bit. Difference. Kind of go their own way. But then it depends on where you want to draw your line to calculate your sensitivity. So like if you go up here, for example, you can end up with much tighter bounds on your differences between the models.
Back to hardware, to remove a lot of the insulating material from the
Yeah.
end wall, did you have, like, did you just find that that was unnecessary in the ProtoDUNE one, or did you have to change the design to, why were you able to do that, I guess?
So I don't know, I was involved in the building of ProtoDUNE one. Yes. But this was the original design, and so the end walls, for example, in ProtoDUNE, you had 4, in ProtoDUNE 2, you had 3. And there was this thing called, there was some observed potential charge up that was on this insulating material. So the idea was it's not known that whether or not that was actually the cause, but it's theorized it was. And so the idea was to get rid of as much of that as you could and essentially simplify it, because this is quite heavy and not exactly easiest to move around and stuff. But here you just need to maintain the structure, which, so you have 2 aluminum bars and FRP box beams, and it gets the job done in terms of your stability and structure. So this is overkill in terms of what you actually need.
Okay, so the insulating was more structural as opposed to.
Yeah.
Well, okay.
Any other questions? I actually have one, if I may just
No,
jump
okay,
in, yeah.
I'm just curious.
So on the analysis side, so
Yeah.
you tried in the neural network, what are the next steps that you see would give you an improvement in terms of machine learning techniques that you apply to this kind of event?
So with machine learning, I feel like, and in general for proton decay and DUNE, I think could probably try to take a similar approach to what Superhay does. So they specifically look at like the de-excitation. So it's heavily based off proton system, and no simulations in proton decay have used that in DUNE because they haven't been robust enough. But I think building something of that nature into machine learning or the study could potentially help, because I mean, that's what they primarily use, and that's never been utilized in DUNE. So you do have those de-excitation photons in DUNE as well. And with vertical drift, you have, what is it, 60–70% more photon coverage. So that could potentially really help a lot.
Last question?
Oh my God, no, it's gonna be it was just curiosity, because I know that the APAs are usually built on ground, and then, but then you have the little shaft to go down.
Yes.
Are they what's that gonna be like, I guess?
So they have this large like cage thing that they put them inside of.
Okay,
And so that's what I observed when I was at CERN. So they put this like meters thing to measure like how much it moves and stuff, and then they ship them by truck from UK to CERN. But they're in this large like crate that protects it. And so that will be what we send down into the mine.